Welcome to an interactive course designed to validate and improve our knowledge of heat treatment. The topic of this course is to explain the issue of indication heat treatment needs on drawings. The international standard for describing heat treatment on drawings dates back to 2001. It is designated as ISO 15787. The second edition of this standard was published in 2016 and the third in 2024. However, the latter no longer specifies any changes. Because the methodology is being unified within the EU, this standard is now available in all EU countries in national versions such as DIN valid for Germany, CSN valid for the Czech Republic, NEN for the Netherlands, or NF for France. However, because manufacturers of parts still work with historical drawings, it can be expected that 100% implementation of this new standard will only be apparent in a number of years. Until then, we must accept that we will continue to encounter heat treatment indication on drawings from both modern and past times. That is why certain knowledge is needed in order to correctly assign heat treatment to the purpose described on the drawing. Although national standards were cancelled after the creation of ISO 15787, they still survive in everyday practice thanks to historical drawings. These were standards such as the German DIN 406, Part 11, Angeben über Wärmebehandlung auf Zeichnungen, the French NFE 04505, Indications de traitement thermique sur les dessins, or the British BS 308 Part 3, Engineering Drawing Practice, Indications of Heat Treatment. Despite the significant effort to unify the designation of heat treatment needs and surface treatment on engineering drawings, these regulations have a very diverse form, and it is necessary to be able to read them correctly. Sometimes they are therefore a graphic challenge, often multiplied by the need for language skills. The picture shows an example of an automotive part made of C45EC carbon steel. The part is to be quenched and tempered with a maximum core hardness of 26 Rockwell, a minimum of 13 Rockwell, a yield strength in the range of 600 to 698 megapascals, and tensile strength 750 to 873 megapascals. Acceptance of such a part in the heat treatment shop means that a complete feasibility check of all data in the drawing must be carried out, followed by the determination of heat treatment parameters that guarantee these values with high reliability. These parameters must also be accompanied by control operations to ensure that the customer's requirements have been met when leaving the heat treatment shop. Another example is a part made of 16 manganese chromium S5 steel, carburized at defined locations on the EHT of 0.6 plus 0.3 millimeters and with the required surface hardness of 700 plus 50 HV1. It should be borne in mind that the abbreviation EHT is the original German DN term for determining the depth of carburizing, while the current designation uses CHD term. It is therefore necessary to maintain some knowledge of the historical context and then transfer this knowledge to the current standardized state. When checking the drawing values, it is also necessary to pay attention to the fact that the drawing specifies the maximum value of residual austenite in the carburized layer up to 15%, as well as the value of the internal oxide layer to a depth of 20 microns. According to the new designation, this value should be marked with the abbreviation IOD, in English Internal Oxidation Depth. Another example is a French drawing for a part made of iron silicon 3P material. In the literature, it can be found that it is a material complying with EN standard 1.3843. It does not occur in the lists of steels. After a long search, it is possible to find out that it is steel alloyed only with silicon with a content of 2.5 to 4% silicon. However, it is equally difficult to trace the conditions of heat treatment. Therefore, it is necessary to strictly adhere to the client's prescription, which is on the drawing. That is, stabilizing annealing in a vacuum under an inert atmosphere at a temperature of 593 to 649 Celsius. However, such a regulation is usually accompanied by the customer's internal specification, and the production process must therefore be adapted to these requirements. In the case of this drawing, it is a nitrocarburizing prescription with a white layer thickness of 10 to 25 microns and a surface hardness of 400 to 640 HV1. However, the prescription for nitrocarburizing can also take other, much more complicated forms. According to the information in this drawing, it is a nitrocarburizing with subsequent oxidation of 41 chromium sulfur 4 material. The designation QT then stands for quenched and tempered, to tensile strength Rm 820 to 1030 Newton per millimeter square. The actual prescription for nitrocarburizing with oxidation is hidden under the designation GNC plus OX, with reference to the internal standard TL187B. At the same time, however, there is a requirement to protect the thread before nitrocarburizing and to polish the surface after nitrocarburizing. The regulation is further supplemented by information on the permissible corrosion resistance of at least 240 hours or 96 hours in the prescribed corrosive environment of salt spray. Therefore, in order to correctly identify the customer's requirement according to the drawing, it is necessary to have language skills. It is necessary to identify 41 chromium sulfur 4 steel. And it is also necessary to know what some abbreviations, such as GNC plus OX or RM, represent. GNC is gas nitrocarburizing. OX represents surface oxidation, and RM is the abbreviation used to indicate tensile strength. However, we must also have an internal customer standard marked as TL187B, where all the essential details of the processing will certainly be listed. However, we must also know how to ensure the polishing of the surface in the market areas after nitrocarburizing, or we must know how to protect the thread as required in the drawing for gas nitrocarburizing. Furthermore, we have to deduce how and where to perform and evaluate the corrosion test in accordance with the requirements so that the results are sufficiently identifiable. Reading the regulations for thermal or chemical thermal designation on drawings is therefore not easy at all and requires long-term knowledge and experience. So, what does the above ISO 15787 standard actually say? This standard states that the following information should be included on the drawing, or a reference to it. Material: heat treatment method described in words, for example, annealing, hardening, carburizing, nitriding, etc. Required core hardness, value and band. Required surface hardness, value and band. CHD depth for case-hardened layers. NHD depth for nitriding layers. SHD depth for surface induction and flame hardening. FHD depth for laser or EBM hardening. CLT surface compound layer thickness. IOD internal oxidation depth, OLT oxide layer thickness, and CD 35 carburizing depth expressed in percent. Other possible data on the drawing are the following information: HTO, heat treatment order, and HTS, heat treatment specification. The actual heat treatment should be defined verbally, for example, quenching to oil, quenching in nitrogen, quenching to oil and tempering, carburizing, nitriding, nitrocarburizing, etc. The description must be clear enough so that the person performing the heat treatment operation performs it in an unmistakable way, with the results according to the drawing requirements. In the context of language translations, it is necessary to draw attention to the frequent confusion of the terms nitrocarburizing and carbonitriding. Especially in the Czech language, completely opposite terms are used. Czech term carbonitridace is equal to nitrocarburizing, diffusion of carbon and nitrogen into ferrite, and nitrocementates is equal to carbonitriding, diffusion of carbon and nitrogen into austenite. If there is a heat treatment requirement on a drawing, some surfaces may be marked with different lines, indicating whether the surface should be, can be, or must not be heat treated. The line type is based on ISO 128-24. The individual surfaces on the drawings are marked as follows. Areas to be heat treated are marked with a long dashed dotted wide line. Areas that may be heat treated are marked with a dashed wide line. Areas that must not be heat treated are marked with a dotted wide line. Areas to indicate the expected or wished spread of the surface hardened areas are marked with long dashed dotted narrow line. If there are areas with different heat treatments on the component, each area must be marked with a mark and a number. A description must be given for each mark and number. If necessary, a control point of measurement can be marked for each area too. And now we will list some practical examples here. In the first case, it is quenching without tempering. Therefore, the drawing will explicitly state that the component is only to be hardened, without tempering to 60+4 Rockwell. The second example is quenching and tempering. Even in this case, a verbal statement is necessary, including the final hardness. In the third example, the measurement checkpoint is additionally specified. This is important for the output control so that the resulting measured values correspond to the customer's requirements and are measured at the agreed location. The hardness designation has its own specifics. The standard distinguishes between hardness for surface and core measurements. The units of measurement are given according to Vickers, ISO 6507, or according to Rockwell, ISO 6508, or according to Brunel, ISO 6506. If there is no other requirement for local hardness values, one value is given for the entire part. If different hardnesses are required at different locations, there will be more of these data. Similar rules apply to core hardness. Since this is a destructive test, the number of pieces allowed for the test must be determined, or a test piece must be supplied. A tolerance band must be prescribed for each hardness value. With regard to the accuracy of the hardness measurement, only one individual value cannot be given. For example, for the Rockwell method, the accuracy is plus or minus 1.5 Rockwell, a total of 3 Rockwell, and therefore the tolerance band prescription should be equal or greater than this value. The measurement location must be marked on the drawing with a mark, or a mark and a dimensioned position. In the case of multiple measurement points, these points must be distinguished by a number. Examples of recording values in Rockwell or Vickers units are given in the table. The designation of the induction hardening layer has the following rules. The layer is always labeled SHD. Depending on the requested depth and the resulting hardness of the material, the minimum load values are selected according to Table A1 of the standard. For example, if we have a layer of 0.5 millimeters and the material has a hardness above 500 HV, the measurement method will be HV30. The recipe for the quenching depth is always given in the drawing, including the required ultimate hardness, measured according to the Vickers method in HV1. It is assumed that the layer to the specified depth will have a limit hardness, which is usually 80% of the surface hardness. This is even in cases where the surface hardness will be measured HRC, HRA, or HRN. The part in the picture has the regulation 620 plus 160 HV30. The hardening depth is defined as 80% of the surface hardness, which is 620 times 0.8, is equal to 500 HV1 and is prescribed at 0.8 to 1.6 millimeter. This means that if we measure the hardness of the quenched layer in the profile, the hardness must still be 500 HV1 at a depth of 0.8 millimeter. Another example is the hardening of this pin. The surface hardness regulation is 525 plus 100 HV10. Since we require a hardening depth of 0.4 plus 0.4 millimeter, then we have to calculate a value of 80% of 525, which is 420. The hardening depth will therefore be SHD 420 equals 0.4 plus 0.4, and it means that there must still be a hardness of 420 HV1 at a depth of 0.4 millimeter. It can also be seen from the picture that if we do not want the edges to be hardened due to, for example, overheating and cracking, we can dimension areas that do not need to be surface hardened. Similar rules apply to laser or electron beam surface hardening, but in this case the layer is referred to as FHD. In the case of carburizing with quenching, the layer is referred to as CHD. If it is carburizing without quenching, then the designation of the carburized layer is just CD. The effective carburizing depth is the depth where we still achieve the agreed hardness of 550 Vickers units, measured by the HV1 method. In this case, the effective depth is not given and is marked with CHD without any further marking. If the ultimate hardness is to be expressed differently than 550 HV1, then a different hardness and load are indicated in the drawing. For example, by the designation CHD 600 HV3 with a carburizing depth of 0.5 millimeter, we mean that at the required depth of 0.5 millimeter, there will still be a hardness of at least 600 HV3. The requirement for carburizing must be verbally expressed in the drawing by the word carburizing. If the carburizing process requires special precautions, the drawing must include the HTO designation and a reference to the appropriate manufacturing instructions. If different values of carburizing are required in different places, it is necessary to mark these places and specify the parameters for them. In this case, it is assumed that the component will be tempered in area 2 with a hardness drop below 550 HV10. In the second case, an example of a requirement for different carburizing depths at different locations is shown. If the carburizing is to be only local, the required area for carburizing is marked with a long dashed, dotted wide line, and the CHD parameters are entered next to it. If the carburizing is to be applied only locally, then the area for carburizing is marked, and it is assumed that the soft part will be masked with a protective paint. It would be appropriate to write entire part hardened on the drawing. If only carburizing is required for subsequent machining, and only after that quenching, then carburizing is prescribed with the CD symbol with a description. The added value of 0.35 means that the carbon concentration in the limit depth will still be 0.35%. The tolerance band of the limit values is prescribed according to Table 9 of the standard. In our case, for the carburizing requirement of 1.2 millimeters, the tolerance will be plus 0.5 millimeter. Nitriding layers are designated as NHD on the drawing, and it is assumed that the diffusion depth is the depth at which a hardness of 50 units higher than the core hardness is achieved, measured at HV 0.5. In addition to this parameter, the layer can also be designated by the description of compound layer thickness, CLT. This data is given in microns. An example is shown in the figure. This is a prescription for plasma nitriding with a required diffusion depth NHD of 0.3 plus 0.1 millimeter and a surface hardness higher than 950 HV10s. The fact that plasma nitriding is defined means that the part cannot be nitrided in gas. These technologies are not interchangeable without customer approval. If the prescription is designated as nitriding, without mentioning nitriding in gas, then both processes are interchangeable. At the same time, however, this description shows how to prescribe a different NHD rating than is standardized. In this case, the diffusion depth is evaluated as the depth where HV 0.3 is used instead of HV 0.5, and 0.1 mm plus 0.05 mm should be achieved. In this case, it is nitrocarburizing, where only a compound layer with a thickness of 12 plus 6 microns is required. The diffusion depth defined over NHD is either immeasurable with respect to steel alloying or irrelevant with respect to purpose. In the second case, it is a similar regulation. It is only defined that nitrocarburizing must take place in a salt bath. For nitrating or nitrocarburizing, only local application can also be prescribed. The surface intended for this purpose is marked with a long dashed dotted wide line, as in the previous cases. Unmarked areas are expected to be protected, either mechanically in the case of plasma or with a protective paste in the case of gas nitriding. The tolerance band for NHD are defined in Table 7 of the standard, the tolerance band for CLT in Table 10. The last chapter is the designation of annealing operations on drawings. These do not have a defined abbreviation and are listed verbally on the drawings. These include, for example, the following terms: stress relieving, soft annealing, homogenizing annealing, recrystallization annealing, or normalizing annealing. However, there are many more of these annealing processes, and it is therefore necessary to read the drawing and any description for it, containing the actual annealing procedure. Not only the temperature can be decisive, but also the method of heating or cooling, and each such case must be approached individually. The indication of heat treatment on drawings course is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive, and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels, so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to SCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a perpetual license for €200 per course. The compressed zip file will be 50 to 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0, on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system, LMS, that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, or even at home. And you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.